Thank you, Session Chair, and welcome to everyone. Today, we would like to present our work as Quantification and Prediction Models for the Impact of POIs on Road Traffic Congestion in Developing Countries, which is the outcome of my graduate thesis under supervision of Dr. Tanjima Hashem and Dr. Mohammad Yunus Ali.
In this presentation, we will see the problem definition, the goals, and the importance of this work. We will also mention some of the existing studies and their limitations. Then, we will give discussion on our methodology. Finally, we will draw a conclusion and the future aspects of this study.
In Dhaka city, Dhanmondi and Panthapot are two of the busiest areas. If we move in other than Tuesday, we'll face congestion like the images on the right side. On the other hand, in Tuesday, we should face freeway like images on the left side. Why is this happening? In developing country like us, before establishing a point of interest as known as POI, like shopping mall, hospital, school, the authority do not consider the impact of POI activities on road traffic. Since the POIs, in this case, mostly shopping mall on Dhanmondi or Panthapot remain closed on Tuesday, normally we don't find any high traffic jam on the mentioned road. If we travel on other than Tuesday, it is almost confirmed that we have to face high traffic jam. In recent years, traffic jam has become intolerable problem in Bangladesh. Statistics have shown that the estimated cost of congestion is 3.8 billion US dollar per year. Also, people lose 1.3 hour only for the traffic jam where their average travel time is 2.35 hours. The time loss is nearly 60% of their travel time. Now, we do know the POI activity has impact on road congestion. However, if a traffic congestion occurs on road, it is not certain whether the congestion is caused by POI activities or other factors like weather condition or rush hour, etc. Therefore, the first goal of our work is to identify whether there is any impact of POI activities on certain traffic jam. If there is an impact, our next goal is to quantify how severe the impact is. We also develop a technique to predict the impact of POI activities on road traffic. Finally, we'll perform case studies and experiments to validate our technique to identify, quantify, and predict the impact. With the help of our work, proper authority can reschedule POI's active time when two or more adjacent POIs have overlapping active time. With prediction, driver can find more free routes with less impact, and also city corporation can find the proper location for new POI by forecasting its impact on road traffic. We define the vehicles that interacts with a POI on its surrounding road as POI traffic. Our first challenge is to differentiate this POI traffic from regular traffic. In a developing country like Bangladesh, it is not feasible to deploy sensors in underground and thereby separate POI traffic from regular traffic. Furthermore, still in our country, most of the vehicles lack proper GPS facility. Thus, we have to rely on manual data collection to approximate the POI traffic, which is the number of vehicles which are interacting to the POI. Recently, there are few techniques which measure the impact of an accident. However, we cannot extend those models because of POI traffic pattern is quite different to accident traffic pattern. We are the first who address the problem of analyzing the impact of POI activities on road traffic. From the previous discussion, we learned that POI activity may have impact on certain road congestion. Now we need to find if POI activity is the reason for a certain traffic congestion. Whenever a traffic flow hampers, it first affects on the speed. That is why we need to calculate speed change with respect to maximum allowable in certain location L over the time spent delta t. However, small speed change don't indicate congestion. That is why we need to set a threshold lambda. When speed change is over the limit threshold, then we can mention there is a congestion. When there is a congestion, it doesn't mean that the traffic congestion is caused by POI activity. The following figure shows a typical scenario where the congestion is created by regular traffic pressure, though there exists some POI traffic which are shown in red blocks. Thus, observing only speed change ratio, we can guarantee that the POI activities have caused the road traffic congestion because there are some other factors like rush hour or bad weather, etc. We conducted field study to identify the traffic pattern when a traffic congestion is caused by POI activity. To observe the pattern, we consider 5 categories of POI. One of them is Bosundhara city, which is situated in Pantopot. Now we will show a little snap as a video how a traffic changes before occurring a traffic congestion due to POI activity. This is a typical scenario of Pantopot in front of Bosundhara city. The right side is adjacent to the POI. In this side, adjacent lanes are occupied by the POI traffic. Let's observe the bus on the right side. It blocks the road segment so that the following road traffic could not get the free flow. On the other hand, the additional vehicles like free rickshaw and CNG wait for the passengers and blocks the road. Hence, in all cases, we have the following observation. When a POI is in its effect period, then its POI traffic affects its adjacent road length more than the furthest length on its adjacent side. On the other side, the furthest lanes are more affected than the adjacent lanes. Based on our observation, we find that we have to focus on the average speed change ratio of every substream, where substream is a random series of vehicles which are moving in uniform speed. We consider substream instead of lanes because the proper lane-wise traffic movement is not observed in traffic congestion. Thus, if speed change ratio is closer to the substream to the POI becomes higher than the furthest, then the POI activity has caused the impact on congestion. However, during our field study, we also observed that speed change of substreams becomes sometimes very similar. In those cases, we have to depend on time headway to identify the traffic pattern. What is time headway? Let us take the rectangle as a car. The car is moved into the front position. The time is needed to cross the lane is called time headway. This time headway gets higher value when people are moving in or out from the PY traffic. Let's get back to our problem. We need to measure each substream speed change, and time headway to help us to find the impact is caused by POI or not. Speed decreases in closer substream, then the congestion is caused by POI. But if the speed change of every substream are similar, then POIs adjacent or further substream on other side have high time headway, then the congestion is also caused by POI traffic. Now we will take a look how to quantify an impact of POI activity on road congestion. During our field study, we observed that the impact area increases within the increase of POI traffic. Specifically, we observed that the impact area expands in both in width and length. Thus, it gradually covers high number of substream and also the length of affected substream increases. And this situation continues as long as speed is slow along with a high time headway. The figure shows us typical congestion when a POI is interacting to its traffic. The boxes represent various impact area per substream. We can measure this impacted length and width of every substream. Thus, we can calculate the area by following equation, where L represents affected substream lengths and WS represent affected substream widths. For simplicity, we consider the width is similar. To get our experimental data, we would consider two types of POI: hospital as popular hospital and diagnostic center, and shopping mall as Bosundhara city. We have taken the weekly based data on these two types of POI. We measure four parameters. Speed and affected stream length comes from the video data. POI is estimated by manual process and then verified with the video data. And finally, the time headway comes from the vehicle passing count in certain time span. Now we show three graphs representing the relation between the hourly basis time span versus the estimated POI traffic. The first graph shows very high values throughout the day as it is weekend day. The second graph is for weekday, which is comparatively less value than the weekend day. And the final graph shows very less value as it is closed day. This slide contains three graphs which represent time span versus substream was affected length. The first graph shows the impact area as the impact value is quite high in the high active time. The second graph shows impact on weekday, which is 15 to 20% less than the weekend day. However, the most significant prospect shows in the third graph, where the impact is around 90% less than the weekend. Furthermore, the first two graphs show adjacent substream and the further substream have the highest impact, which validates our observation. Now we will describe briefly about our prediction methodology. The input to the prediction model are POI category like shopping mall, hospital, estimated POI traffic, and substream wise speed change and time headway. Our model will predict the impact of POI in terms of affected area. We use fuzzy linear regression to develop prediction model, and fuzzy coefficients are involved in our model change based on the POI category. Next, we show how we categorize the POI based on different attributes. We identify the POI traffic as predictable and non-predictable like shopping mall and hospital, etc. For the predictable ones like school and office, etc., we can estimate the POI traffic count from the historical data. The interactive traffic count is more or less constant to the POI like school and office. On the other hand, POI traffic may changes based on the interaction like schedule basis as transport facility or even driven as religious places. Moreover, we need to consider POI's own attribute set as having parking facility or not. As we have already mentioned that we use fuzzy linear regression for our prediction model, now we will give a brief overview of fuzzy linear regression. The basic fuzzy linear equation is shown in equation 1, where y is the fuzzy output, x are the real inputs, and a are the fuzzy coefficients. The fuzzy coefficients can be described on center, alpha, and spread c on the basis of their membership function. Therefore, the equation can be rewritten as equation 2. Now we compute this center and spread by solving the linear programming problem. We will show in detail for solving this problem while describing our prediction model. Since our output is also fuzzy, it can be expressed using a membership function. This membership function will give lower bound, center, and upper bound for our fuzzy output y. Therefore, our output consists of three bounds, where the lower bound is the YL, the center is Y, and the upper bound is YU. For the lower bound, we use center minus spread, and for higher bound, we use center plus spread. On the other hand, centerline uses alpha only. Now we will describe how our prediction model works. Just to remind us, we take POI category, estimated POI traffic, and substream wise speed change and time headway. Our prediction is the impact area where we forecast the substream wise impacted length. Then we sum this length and multiply with average variance curve with to find out the impacted area. In the fuzzy linear equation, we replace x parameter with the traffic parameter npoi, delta v, and th. Our models learns alpha and c in training phase and use them in prediction phase. Now we will see how our model learns alpha and c. Without loss of generality, let us consider an example where traffic data for four different time t1, t2, t3, and t4 for a definite substream I. Earlier, we saw the linear problem to find out the fuzzy parameters. Our objective is to minimize spread on the real data input set and solve the presented inequalities. There are 12 equations and 8 unknowns. Therefore, we can easily compute the spread and center set by solving this linear programming problem. Our prediction works on two steps. First, it identifies whether there is any impact, and if yes, then our model quantifies the impact in terms of affected area. Now, using the dataset from both fuzzy and real parameters, we can find our fuzzy output, where the upper bound and the lower bound is calculated for h equal to 0.5. Then we inject h equal to lambda to find the projected length. Let us consider another example where the total road length is 250 meter. In first case, for a certain substream, upper bound is 100 and lower bound is 20, and our projected impact length is 15 meter. So we call there is no impact here as the projection falls below the lower bound. Again, in the second case, upper bound is 175 and lower bound is 95, as our projection is 140 meter, which is in the between of upper and lower bound, so we can say there is impact of POI activity. In third case, upper bound is 250 and lower bound is 200, and the projection is 255 meter, which falls over the upper bound. That indicates there is already a congestion which has the POI impact also. Let us see the above scenario in a flowchart. First, we check the estimated POI traffic is available. If not, we say there is no impact. Else, for each substream, we compute the lower bound and the upper bound and the projected output. Then, if the projected length is less than the lower bound, then there is no impact. Otherwise, the substream has impact on POI activity. Then we check any substream has any impact. If it is no, then we say no impact. Any of them has impact, we can compute the impact area with this following equation. We use 70% data to learn and rest 30% data is used to check accuracy. For both POI, we train up our model with Sunday and Monday data and test accuracy with the Wednesday data. Now we will see the graphs represent the accuracy of our model. The left and the right side represents the error of forecasted impact length for Popular Diagnostic Center and Bosundhara City respectively. The x-axis represents hour-based time span and y-axis represents stream-wise length error. For hospital, the early time span have very less error, which is less than 12%. Then, a middle time span gets higher because the nearest POI City College activity. Actually, City College is very close to Popular and we don't consider POI traffic of City College. Again, in its high active time, our model works well as error rate nearly 10%. On the other hand, for shopping mall, our model shows good prediction throughout the whole day as it shows error around 5% except the last two time span. During 8 to 10 p.m., traffic stays same place for a long time. Thus, our prediction model confused whether it is road traffic or POI traffic. In summary, we propose a model which can identify and quantify the impact of a certain POI activities. We will also predict the impact to identification and quantification and to validate our model's accuracy. Do you have any question? We're glad to answer that. Finally, thank you to all.